to do is to go to yeah. So I'm gonna put the material here. So I haven't uploaded anything for day 2, day 3, and day 5. Day 1 is more or less complete. I've put some stuff in day 2 and day 5. It's not complete yet. Yeah. And then I was thinking of having some paper presentations at the end of the class on Friday. So I've compiled a list of papers. Let me show them here. Yeah, I've compiled a small list of papers, a short list of papers. So it would be nice if you could volunteer for and present these papers at the end of the class on Friday in the afternoon. So some of them are actually just pure machine learning papers, but some of them are about applications in astronomy. So you have, so the first one is dropout, and we will talk about it tomorrow. So the second one is about using Gaussian processes to estimate the parameters of stellar rotations. So we will talk about Gaussian processes on Wednesday. No. Actually, not Wednesday. Thursday. We will talk about it on Thursday. And then we won't talk about this at all. Adversarial attacks on neural networks. It's a hot topic these days. It's basically about how to fool the neural network. So you introduce some impurity or contamination to the data, to the input data, and then you can use this to fool the neural networks. So it's a very hot topic of research. So for instance, you have a picture of a panda, right? So if you give a picture of a panda, it's a clean picture of a panda, and you give it to a famous neural networks like AlexNet. We will talk about it on Wednesday. It'll tell you that this picture is a picture of a panda with, I don't know, 99% confidence, right? But then adversarial attacks basically tells you that, yeah, if you add noise to this image of a panda, right, then the network is gonna give you a totally different label. It's gonna tell you this is like a, I don't know, alligator with not a panda, with another confidence interval. So this is a very hot topic. And then the fourth one is XGBoost. So we will talk about decision trees today, but XGBoost is a very powerful method for doing decision trees and for combining models. Almost everyone uses XGBoost these days. So we're not going to talk about it in the class because we won't have time for sure. But then it would be nice if someone picks this up and then talks about it. It's a very brief paper, and it's easy to follow. This one is a bit more technical. So this is about using convolutional neural networks to predict structure formation, cosmological structure formation. And then this paper is about doing outlier detection in the SDSS spectroscopic data. And then this one is a very old paper. It's about star galaxy separation with support vector machines. Again, we won't have time to go through support vector machines in the class, but yeah, if someone picks this up, then we can all learn about support vector machines as well. And then the last one is a bit more technical. It's a pure machine learning paper. It's about Adam optimization. We will talk about the optimization methods in deep learning tomorrow, but we're not gonna go much in depth. So it would be nice, again, if someone picks this up and then talk about Adam. It might be a bit technical. Like whoever picks, like for instance, this paper doesn't have to go through in all the details, but yeah. It would be nice actually. Then, if you read this paper, you get some intuition about how the optimization works, and it's actually kind of nice. Yeah. So these are the list of papers. So if you're interested in presenting in any of these papers on Friday, just send me an email. You can also form groups. You don't have to do it individually. You can team up with 2, 3, even 4 people and present one of these papers on your own. Just let me know. Just either let me know or send me an email. So yeah, these are the papers. And as for the format, we won't have a dedicated exercise per se in the afternoons. So the afternoon sessions and the morning sessions are going to be the same. So we will just go through notebooks. So for instance, for day 1, I'm not going to show any slides, but for tomorrow and the day after tomorrow, I'm going to show some slides for deep learning and convolutional neural net, because it was hard to explain them on a piece of Jupyter notebook. So basically, the format in the afternoon and the morning is going to be more or less the same. So we're just going to go through some code. Hopefully, you can just go on Colab and modify the code and run it on your own. And when you're on your own, you can maybe modify here and there and see how the outcome of the code changes, right? So let's see. So I think that's all. And then we can get started now. Okay, so let's yes. This one, where is it? Is it this one? No, that one. Better now? Yeah. Yeah, so I'm going to ask Esteban to put the list of papers on the internet, on the website, so you can go and check them out. Okay. So let's get started. So if you all go to this GitHub repository, you all have the link, right? So can you go to day 1? And then once you're in day 1, can you go to K nearest neighbors? Can you click on this one? So once you're in K nearest neighbors, okay, so once you're in the K nearest neighbor, just click on Colab. I'm actually curious as to how it works. Let me see. It's still loading. Okay, nearest neighbors. Okay, so can you edit it as well yourself? Can you run this? What does it say? Okay, perfect. You're connected as well? Yeah, perfect. Yeah, I think you need to click on that, yeah.
I prefer you copy.
Yeah.
Copy my drive.
Oh, yes, I guess you can also do that, yeah. Yeah, you might have to copy it on your Google Drive, yeah. Maybe it works better. Yeah, copier and drive, yeah. Let's see. This is still loading. So you're already connected, but did you copy it in your drive? Yeah, maybe you can also copy it in your drive. If you click on copier and drive, yeah. Let's see. Oh yeah, so now you can click on this, open in Colab. So you're already connected. Oh, you copied it in your drive, didn't you? Yeah. Okay, great. Let's see. So can you run to see if it works? So you're already connected, aren't you? Yeah. Does it work?
Yeah.
Okay, perfect. Yeah, and for you as well. Okay, perfect. Yeah. Yeah. Were you able to connect?
I know, but I don't get you.
Oh, okay, yeah. All right, so did you all manage to connect? Okay, yeah. Then, yeah, if you can also maybe click on this to copy it on to your own drive, but I don't know, maybe it's not necessary actually. I'm not sure. As long as you can run the code on your own, it's fine. Maybe you don't have to copy it in your drive. So, yeah. So we're going to start with k nearest neighbors. It's basically one of the most trivial algorithms in supervised learning. It's actually quite simple. You don't need to know that much math. So let's say you have a bunch of data. So let's say you have a bunch of data, right? A bunch of like stars and a bunch of circles. Right? So the way it works is that let's say you have two features, x1 and x2, right? And you have a bunch of labels, stars and circles, right? So you introduce a new point to this system, like let's say you pick this point, right? And then you say, what class does this new point belong to, right? So it's actually quite simple. So what you do is that in k nearest neighbor, what you do is that you just draw a circle or a sphere. If you're in a multi-dimensional space, you just draw a circle around it, right? You like do this, like draw a circle, right? And then the way you draw the circle is that you say, I want 5 nearest neighbors to be in this circle or multi-dimensional sphere, right? So let's say you pick the nearest neighbors to be 5, right? And then you count the number of training examples in this circle, right? So the probability that the test point belongs to the class, to the star class, it's you can compute it quite simply. You just count the number of stars within this circle, right? And you just divide it by the number of nearest neighbors, which is like 5, right? And then the probability of the test point belonging to the class circle is basically just this, right? It's quite simple, right? So the way it works is that you compute the distance between the new points and all these training examples, right? And then you say that you want to have, I don't know, let's say 5 nearest neighbors, and then you draw a circle or a sphere here, right? And then we can compute these two probabilities, right? And then so these are probabilities. We want to know what is the best estimate of this estimate of the label of this new point, right? So the best estimate of the label of this new point is simply just the class that gives you the highest probabilities, right? So in this example, how many stars are there? 4, yeah. So this is 4/5, and how many circles are there? Yeah, just 1. Yeah. So this is larger than. So this is larger than this one. Therefore, you say that the test point, the label of the test point is y of is basically a star, right? So yeah, that's nearest neighbors. It's quite simple. It works very well when you have dense features, right? So, and by dense features, I mean like you have like numbers, continuous numbers between some minimum and some maximums, right? But then when you have like discrete features, let's say you have like 0, 1, 2, 10, it may not work that well, right? But it works very well when you have like dense features. Yeah. So let's go through this example. So yeah, so the first one, yeah, you just basically import some libraries. Let me do it as well. Let's hope it's not run anyways, not authorized, run anyways. Yeah. So then here, yeah, basically what you do is that, yeah, you make 2 blobs of points, 2 clusters of points with different labels. Right? And then basically in the first lines we make some blobs of points with 2 labels, 0 and 1, right? And then we introduce some new points, which is a test point, and then what we want to do is that we want to figure out what this test point belong to. So we go to here, so here basically this is just a scatter plot. So yeah, so we have 2 classes, we have zeros, these are zeros and these are ones, and we have some label. This a star, I don't know if you can see it here. Can you see it? Yeah, so this is a label, and then we want to basically figure out what this label belongs to. What class does it belong to, right? So here is a bit of a math. Basically, you just count the number of within the multidimensional sphere. You just count the number of yellow points, and you count the number of purple points. And these probabilities are basically can be computed by just counting the number of points, right? The yellow points and the purple points. Is it clear? So you go here, and now, so here basically what we do is that for a test point, so here the test points. So in this function, the point is the test point. Is a point that we want to find its label of, and x's basically these are the data, the training data, right? So this function basically returns you the radius of the sphere that contains the k nearest neighbors, right? So this function pairwise distance basically computes the distance between the pairwise distance, just compute the distance between this test point and all these points, right? And then, so this simple function basically returns you the sphere that contains the k nearest neighbors, right? And so this shows that you can actually implement the k nearest neighbors from scratch. You don't really need to use any library, but it might be faster. So they do some, so if you go to the scikit-learn implementation, so they use some smart things. You don't have to calculate the distance between the test point and all the points, right? Necessarily. But here we're just gonna do it. It's gonna be fine. And so this so here in this function, basically, yeah. For a given list of k nearest neighbors, this function basically just draws a sphere around the test point. Let's do it. Now, if you draw a sphere, so you have this sphere and this sphere, right? And then the way k nearest neighbor works is that you just count the number of nearest neighbors within the sphere, which one belongs to class 0, which one belongs to class 1. The one with the majority of the points is the winning class, right? So here you can, in the function, I encourage you to change these numbers to see how it works. So for instance, you can just change these numbers to whatever number you want, like, I don't know, 100, 200, even 1. Yeah. So what happens is that if you choose the number of nearest neighbors to be like 1, right? Then your algorithm will basically just learn, will memorize the data, will memorize the training set. It will just, if you set the number of nearest neighbors to 1, right? Then the algorithm does something quite simple. It basically looks at the nearest neighbors. It says, if it's a star, then the test point is a star. If it's a circle, then the test point is a circle, right? So you have this freedom at choosing the number of nearest neighbors, right? But then the problem is that what number of nearest neighbors should I use for a given problem? And that's what we're gonna discuss now, right? So let's load this. So what this does is that, so this function in sklearn train test split, what it does is that you give it a set of data and a set of labels, right? A set of features and a set of labels. And then what it does is that it splits them into a training and a test set. So in machine learning, what we are interested in is that, so we train the algorithm with a number of trainings, with a number of training data sets, training examples, and then we introduce a bunch of new examples. These are the test examples, right? And then we want to evaluate the performance of the model using this test sets, right? So that's how you can basically evaluate the performance of the model. So here we just, so in this cell we just split the data into training and test, and then we load this library k-neighbors classifiers, right? So let's go down. All right. Yeah, so here you can, so here you can initialize the model, the number of nearest neighbors. You can set it to whatever number you want. Feel free to change this number. But the point is, when you fit the model, basically what the nearest neighbor classifier does is that it creates a lookup table. It just basically computes the yeah, basically it basically just memorizes the locations of the points and their neighbors and their labels, right? And then when you want to predict the label of a new test data, what it does is that it computes the distance between the test point and the training points, right? And it draws, and then it draws a circle containing the k nearest neighbors, and then it counts the class that has majority of the examples within that sphere, right? And that's how the prediction is done, right? So now if you run this cell, you can compute the training accuracy and the test accuracy. We don't really care much about the training accuracy. What we care about is the test accuracy. So basically the accuracy in the test set tells you that if you introduce a new point, a new test point to the data, with what accuracy can I estimate its, can I predict its label, right? and something like 94% accuracy, right? But then, yeah, so feel free to change this number to see how the test accuracy changes. So you can set it to 1, yeah, or 10 or whatever, and see how this number changes. And then we will talk about accuracy later in the course. Today, actually, today we'll talk about accuracy. So, and other measures of success. So the number of nearest neighbors is 6. So yeah. So now the question is that what number of nearest neighbors should I choose, right? So that's the question. If you set the number of nearest neighbors to 1, as I said before, the classifier is going to memorize the training set, right? It just looks up the training set, looks at the nearest neighbor. If it's a star, then it assigns the star to the label. If it's a circle, then it assigns circle to the label, right? So let's visualize this a bit to see how it works. Oops. So this function, decision boundaries, what it does is that it takes the training set and it takes the training features and then training labels and some grid size and the model. The model is the model that you've trained on the data already, right? And then what it does is that it creates some decision boundaries. For instance, it's gonna say this region belongs to the star class and this region belongs to the circle class. So this is just a very simple task that this model does. So let's look at how it works. So if you run this, so you have a decision boundary function, and then you have a k nearest neighbor model that basically takes as an input at the training features, the training example, and the number of nearest neighbors, right? And it just fits the model and then returns the model. And this is the model that you will have to put here to be able to visualize the decision boundaries. So let's do this. So now I want to visualize the decision boundaries for different number of nearest neighbors. For instance, 1, 5, and 10. Again, feel free to change these numbers to gain some intuition about how this works. So for instance, we can change this number from 10 to whatever, 100 or 600 or whatever, to see how it all changes. So if I run this cell, yeah. So if you have only if you pick a model with the number of nearest neighbors equals to 1, what you see is that the decision boundaries are very noisy. And the reason is that this model is very complex. It may sound counterintuitive, but if you train a k nearest neighbor classifier with just 1, with the number of nearest neighbors equals to 1, the behavior of the model is going to be very complex because it's always going to look at just one nearest neighbor, and then it's going to assign the label according to the label of that one nearest neighbor. So for instance, here you have like the decision boundary is not very smooth. That's why you have all these like fluctuations here and there. And like here, I don't know if you've seen like you have some like yellow areas, like islands within this purple area, right? But then if you increase so if you look at also the test accuracy, so basically the test accuracy tells you how accurately you can predict the label of a new example that the model hasn't looked at yet, right? So it's 90%. So if you increase the number of nearest neighbors, the accuracy increases a bit. And as you can see in this new model, the decision boundary is a bit more smooth. It's smoother than before, right? And then you have less of those islands in the middle, right? And then if you increase it even further, it becomes even more smooth, right? And then you just completely get rid of the islands, right? So a nearest neighbor classifier with a number of nearest neighbors set to 1 is actually a very complex model, right? And it doesn't necessarily give you a good test accuracy, but that's something that is totally problem dependent, and that's what we want to figure out now, right? So as you saw here, the test accuracy increased as we So when the number of nearest neighbors was 1, the test accuracy was something like whatever, 90%, and then it increased a bit, like 93% or something, right? So you have here, and it becomes like this, 4, 5, and 10, right? So feel free to change these numbers, like you can change, I don't know, 10 to 100 and see, just visualize how it works. Like it gives you more intuition as to how the classifier works. So how do we set the number of nearest neighbors? So that's the question. Let's see. Okay, so the way it works, so the way we choose the so in any machine learning classification or in any machine learning algorithm, we have a number of parameters and a number of hyperparameters. So the number of nearest neighbors here is an example of a hyperparameter. So the way we set the hyperparameters, the best value for a hyperparameters is the following. Get the time, we're doing good, yeah. So let's say you have a data set, right? And then what you need to do is that you always need to have a test set to just evaluate the performance of the model, right? And then for the training, you should never touch this sorry. This is the test set, right? This is the test set. And then you have a training set that you train the model on, right? But then the question is, how do I set the, let's say you have different models. You have models with different hyperparameters, models with different architectures. So for instance, tomorrow we're going to look at just simple deep learning models. So for these models, you have to choose the number of layers in the neural networks. So how do you choose the number of layers in the neural network? Or how do you choose the number of nearest neighbors in a simple k nearest neighbor classifier? So what you do is that you take the training set and then you split it further into a training set and a validation set. Validation set, right? So the training set is used to just train the model, right? And then for the this is for training the model. And in the validation set, basically is used to choose the best hyperparameters of the model. So for instance, the number of layers in a neural network, in a deep neural networks, or the number of neighbors in the k-nearest neighbor classifiers. Whereas we see later today, the depth of the decision tree, right? So this is something that you need to choose with the validation set. And then the test set is the set that the model has not looked at yet, right? So you haven't trained the model, or you haven't validated the model on the test set. So these are examples that the model has not looked at yet, right? And you want to eventually look at the performance of the model using the test set, right? So So with the training set, you have some like cost function. Usually in the nearest neighbor classifier, you don't have any cost function, or you have some accuracy or some error. So this gives you some error, but it doesn't really matter. So you basically you define some cost function and you minimize it in order to train the model. With the validation set, what you do is that you look at some sort of score, some measure of the success of the model, and we're going to look at this further today. But for now, let's just imagine that this measure of success is accuracy. Accuracy, right? And then with this accuracy or any other measure of success, we're going to pick the model that gives you basically the best accuracy, the best performance in the validation set, right? So, for instance, in the example of nearest neighbor classifier, we look at, we eventually pick the model that gives you the best accuracy in the validation set. So you pick the number of nearest neighbors that gives you the best accuracy in the validation set. And then eventually once you're done, once you've already like picked your like best model, right? So this is like you pick your model. Then you test your model, test the performance of the model with the test set, right? So now let's look at the example of the nearest neighbor classifier. So we want to split the data into training, validation, and test, and then use the validation set to pick the best, the model that gives you the best accuracy, right? So how do you do this splitting? So if the size of the data set is moderate, like let's say you have like 10,000 or 1,000 or something, 100,000, what you do is that you do something like a 70% training, maybe like 80 or whatever, 80, even 60%, and then 10% for the validation, and then 10% on the test set, right? But then if you have a very large data set, like let's say you have like 1 million examples or 10 million examples or something like that, you want to use as much data as possible for training the algorithm. So in that case, you set the number of training examples to 90 whatever, you can like 98%, and you can just allocate 1% to the validation set and then 1% to the test set, right? So in this in this particular example, we don't have that many we don't have that many data points, so we just split the data into, actually I forgot what I did here. I think it's 80%, 10, 10. Let's see. Yeah. So first, so in this cell, basically, yeah, I think 60, 20, 20. That's what I do here. Yeah, 60, 20, 20. So first, I split the data into test and training and validation, right? In this line, right? So you have a training, validation, and then test. And then I take the training and validation and I split it further into a training set and a validation set, right? So this will give you 60% of the data in the training set, 20% in the validation set, and 20% in the test set, right? So if you do this, it's gonna like do this, and then I want to pick the model that has the best, that give me the best validation score, right? So first I make a list of the number of nearest neighbors. So for instance here, I say the number of nearest neighbors is between 1 and 20. So the integers, the list of all the integers between 1 and 20, right? And for any, for every hyperparameter, I train the model, I initialize the model, we can initialize the model, and then we can fit it, and then we can compute the validation score using this. using this attribute called a score, right? And then once you have the validation score for all these hyperparameters, you can pick the one that gives you, so numpy.argmax basically gives you the index of the one that has the highest validation score. And then the best model is the model, that gives you the highest validation score, right? So let's run this to see what it gives us. So so according to this, the model with the model that gives the best validation accuracy is the model with 12 nearest neighbors, right? But as you can see, this curve is very noisy, right? So in the beginning, you're it's like kind of low, but then it becomes lower and it becomes high, and it fluctuates a lot, right? If you run this piece of code yourself, I think you're going to get a different looking. You're going to get a curve that looks differently, and that's what we're going to talk later and how to deal with this. So can you run this yourself and tell me if you get a different answer? So first, run this. So in this function, train, test, split, there is some random seed, right? If you set the random seed to some number, it's always going to give you the same answer. But if you don't choose the random seed, it's going to give you some random, it's going to assign some random subsample of the data to the training set, some random subsample to the test set, and some random subsample to the validation set, right? So if you run this this cell yourself, you're not going to you're not going to get the same training sample as I got. So I encourage you to run this yourself and then look at the validation score and see if it looks the same or different than what I got here. So for instance, I can do this. Let me run it again. Yeah. So now the number of nearest neighbors is totally different for me. It's like 18. What did you get for the number of nearest neighbors? For the best hyperparameter, what did you get? Oh yeah. So if you don't change if you set the random seed to some number, right? It's always going to give you the same training example, same test, and then same validation. But if you don't set the random seed to anything, it's just going to give you some random subsample of the data. But I'm curious as to what you got for this plot. Did you get the same, or did you get a different?
17.
17. Yeah. Yeah. So it's different, right? So, and the problem is that the problem with this approach. The problem with this approach is the following, right? So the data that we work with is noisy, and it has a finite sample size, right? So if you shuffle the data again, and pick another random subsample up from it, right? It's going to give you a different validation set, right? And then the number of nearest neighbors that is favorable by the new validation set is going to be different, right? So that's why this approach may not be the best approach for picking the number of nearest neighbors, because of the inherent noise in the data, right? So since the data is noisy, it has a finite size. If you randomly pick a validation set from it, it's going to look differently. It's going to look different than the validation set that you've picked before, and it's going to give you a different validation score, right? So the solution, one solution that can help us resolve this issue is the following, right? So let's say you've already divided the data into a training and a test set, right? So you have a training set which contains 80% of the data and the test set, right? So the test set, we're not going to touch it at all, right? So the test set is just there for evaluating your model, for setting the hyperparameters of the model. You should never touch the test set, right? Because this is what eventually you want to use as a way to look at the performance of the model, right? So this is a test set, it's a completely separate thing. And you have a training set, which is here, right? So the answer to this, so the solution for this problem is the following. So you take the training set, you divide it to, let's say, 5 equally sized, they don't look very equal, but it's okay. So you divide it into 5 equal sized partitions, right? And then you can you can then do this like 5 times. So 1, 2, 3, 4, 5. Etc. Right? So these are equally sized partitions of the data, right? And then this method is called the k-fold cross-validation. So here I have 5 partitions, so this is a 5-fold cross-validation, right? So then what I do is that, so for this training set, we drop the first portion of the data, right? And then we train the model using this, the remaining 4 partitions, right? So we use this for the training, and then we evaluate the training score using this partition, right? So this gives you some cross-validation score. We call it the cross-validation score. So this gives you some CV score 1. And then in the next step, we drop the next partition, we drop this, and then we train the model using the remaining 4. And then we do the same again and again and again. So we drop this one, and then we train the model using this. And then here we drop this one, and then we train the model using these partitions, and so on, right? And then we do this as well, yeah? So this gives you 5 numbers, 5 cross-validation scores, right? And then we want to use these cross-validation scores. We want to use these cross-validation scores to pick the best model, right? To pick the best number of nearest neighbors. So how do you think we should go about doing that? How do you think we should? How do you think we should use combine these numbers to pick the best model? Any suggestion? Yes, yeah. Basically the mean of the results. So you have 5 cross-validation scores. You just take the mean, the average, right? And then the average gives you. This is very long. The average gives you the model that gives you the best average cross-validation score is the best model, essentially, right? And so this sort of like, if you take the average between all these cross-validation scores, it sort of acts against the noise that is inherent in the data. It acts against what you see here, right? Because you've taken different portions of the data to validate your models, right? So, and if you take the average is more robust to the noise in the data. So, in order to pick the best model, it's better to use the k-fold cross-validation than just doing a naive thing like this, right? So this is called the k-fold cross-validation, and the example here shown here is a 5-fold cross-validation, right? So let's show it let's run it for the nearest neighbor classifier that we have here. Oops. Sweet. Okay. So again, so you can read this later if you want. It's just what I described here. Okay. Oh yeah. So one thing that I forgot to explain is that so you pick the best number of nearest neighbors using this cross-validation score, and then what you do is that you train the model. So this gives you the best number of nearest neighbors, right? The n best, right? Sorry, like k best, right? And then once you have the best estimate of the number of nearest neighbors, you train the model with the entire thing, with the entire training set again. And then once you have the model trained with the entire training set, right? Then you can evaluate the model using the, look at the performance using the test set, right? So first you use the cross-validation to pick the best number of nearest neighbors. Then once you have this, you train it using the entire training set, right? And then you look at the test set. So let's look at this. So here, yeah, you can import the cross-validation score, right? So here, for instance, I'm using 10-fold cross-validation, right? So this is the entire training set and the labels, right? And then you have a 10-fold cross-validation, right? And then this gives you a list of scores, right? So the outcome of this is the list of scores. So if you have if you put the number of cross-validation folds to 10, this gives you 10 numbers, right? So if I put it 5, I'm gonna get 5 numbers. If I put 20, it's gonna give me 20 numbers, right? And then the cross-validation scores that I will care about is the average, is the mean of these numbers, right? So I'm going to compute the mean, and then I'm going to compute the standard deviation, the uncertainty around of these numbers, right? So if I do this, then the cross-validation score is going to look like this. So as you can see, this curve is much smoother than what we saw before. So the one we saw before was very it had a lot of fluctuations, right? But this is like the mean. This is the mean of all these different ways of partitioning the data, right? So as a result, what you get is much more smooth. But then the second thing that you can notice here is that there is a lot of scatter around the mean, right? And this is what we saw before as well, right? If you pick a different validation score, if you pick a different validation subsample, you're going to get a different validation score, right? That's why there is a lot of fluctuation, but the mean, the average cross-validation score itself is robust, is very robust against these fluctuations, against the noise in the data, right? And now if you look at so the best model is the model with 18 nearest neighbors here, right? And then the accuracy that you get is like 93.5%, right? And then if you look at the boundaries look very smooth, right? So let's move on. So another important thing is the scaling of the data. So in machine learning, it's always important to scale the data. We're not going to have enough time to talk about the pre-processing and the scaling and things like that. If you have any question, you can always come after the class and then we can talk about it. But then, yeah, for the machine learning algorithm, it's always important to scale the data, to have the data to vary either between 0 and 1, or scale the data such that the mean is 0 and variance is, the mean is 0 and the variance is 1. So these are different conventions, right? So for instance, in the computer vision, what people usually do is that they just divide. So let's say you have an image, right? You have an image, and what a computer sees is basically a number of a bunch of values and a bunch of pixels, right? So let's say the maximum is like 150 or something. You just divide the number of all the values by 150, so that the range of values of your range of brightness values are always between 0 and 1, right? The problem is that in k nearest neighbors, if you don't scale the data, you might actually get a different answer. You might get a different decision boundary. Do you know why is that? Do you know why you would end up getting a different answer if you scale the data? Yeah.
The shape of the eye looks very different.
Yeah. No, but just in a simple, forget about images. Let's say you have a two-dimensional data, right? So, like you have x1 and x2, and then you want to run the k nearest neighbor algorithm. Why does it matter if you scale or why would it matter if you scale or not scale the data? It's because of the distances, right? Because in k nearest neighbors, what we do is that we compute the distances between the points, right? So let's say you want to estimate the label of this new test point, right? What you do is that you compute its distance to this point, and to this point, right? Within some boundary, within some sphere, hypothetical sphere, right? And then the label with the majority of the examples is the winner, right? But then let's say I scale the data. Let's say I make the data x1. So this is, let's say this is between 0 and 1, and this one is between 0 and 1. But let's say I do something violent to the data. I make it a scale between 0 and 100 along the x-axis, right? So it's going to look like this. Whatever, yeah. Now, if you draw a circle around the test point, right? You're gonna get different examples within the circle, right? So that's why it's nearest neighbors is actually sensitive to a scaling of the data. So it's always good to scale the data in the k nearest neighbors, and that is because, so in practice you might end up with a data set that has very different scalings along different axes, right? So let's say you have a data set with the colors of objects that are measured from photometric band passes, right? So along one of the colors ranges from 0 to 4, but the other color component ranges from 0 to 1, right? Then the distances along the first axis are going to be very different than the distances along the second axis, right? So when your distances along the different axes are so different, you're going to get totally different answers. So that's why it's always important to scale the data between 0 and 1, so that the different axes have the same sort of scaling, right? So here is just the same, yeah. So if you run the data with and without the scaling, you might get different answers, right? So let's see. Yeah, I think we're done with the k nearest neighbors actually. That's good. Yeah. So we have 40 minutes. I think we can go through the. Let's see. So we can go to the decision trees because it should be short. No. So if you go to the GitHub repository again, you go to day 1 again. Now you can go to decision trees. Start run out. And then once you're done with one of the Jupyter notebooks, please restart it so it frees the so it can make the resources free. Just go to insert and then just restart runtime. Don't click on this. If you restart and run out, it's just going to run everything again. You don't want that. Yeah, just restart run, and yeah, and then you can close it. Yes. Decision trees. So once you're in the decision trees, you can open the Colab again. Have you all been successful in opening the Colab? Yeah? Good. So, yeah, okay. So decision trees, yeah, are widely used in machine learning. So let's say you have a data set with 2 or more labels, right? And you have a set of features for the data, right? So what the decision tree does is that it starts splitting the. Would have been a disaster, yeah. So what the decision tree does is that it splits the data based on one or a combination of features, right? In order to find the decision boundaries between the different labels, right? So let's say. So let's say you have a data set like this. This is x1. This is x2 again. And you have a bunch of data points here and there. So you have here. And you have a bunch of circles here. Right? And then you want to obtain the decision boundaries between the data. So the decision tree, what it does is that it recursively splits the data into branches such that eventually you end up with only one of the labels in a given branch. So let's say this is x1, this is x2, and you want to find the decision boundary between the circles and the crosses. So what the decision tree does is that it asks this question. So is x1 greater than 0.5, right? If it's greater than 0.5, it splits the data into a bunch of data points with x1 greater than 0.5 and x1 less than 0.5, right? So what you end up with is so let's say this is 0.5 or something, roughly speaking. So it splits the data into these this portion and this portion, right? So in this portion you have 1, 2, 3, 4, 5, 6, 7, 8 crosses, right? And yeah, and the zero circles, right? So when you only have like 0 circles, and if so, what we call this is called the node, and this is called a branch, basically, and this is also a branch, and this is the top node, and this is the basically a sub node, right? And then what you have here is that you don't have any more circles here, so this one doesn't need any further branching, right? But then you look at this, and then this one has 1, 2, 3, 4, 5 circles and 5 crosses. So you have 5 circles and 5 crosses, right? And then you can ask this question: is this data, if x2 greater than 0.5 or not? So if the x2 is greater than 0.5, if x2 is greater than 0.5, you're going to end up with 5 crosses and 0 circles. So you have 5 crosses and 0 circles. And if x2 is less than 0.5, you have 6 circles and basically 0 crosses, right? You have 6 circles and 0 crosses, right? And then since these two, since this one only contains crosses and this one contains only circles, they don't need any further branching, right? So you end the branching of the data. So basically, this is called a decision tree with a depth of 2. So this is the depth of this. So this is a decision tree and has a depth of 2. And you end up with this boundary between the two labels, right? So you end up with these two boundaries between the two labels. So the question is, based on what criteria should I split the data, right? And what depth should I use for the decision tree, right? So yeah, let's look at that. Let's look at how it works. Yeah. So for this example, for this notebook, I decided to use a very simple data set. It's called the core evaluation data set. Basically, what you have in it, it's far from anything you would have in science, but it's a very nice example to give you, that gives you intuition about how decision trees work, right? So what you have in the core evaluation data set is that you have 1,700 examples, 1,700 examples, instances. And for each instances, you have 6 categorical features. So features can be either categorical or dense. So dense features are the continuous features, right? So let's say you have a variable that continuously varies between 0 and 1, that is a dense feature. If it's categorical, it's distinct, like it's either 0 or 2 or 1 or whatever, right? So it's a categorical feature. So, and you have a label. So for each card you have a label and you have a number of categorical features. So the categorical features are basically, yeah, simple stuff. What is the price of the car, the number of doors, the space for the luggage, safety, etc. And the labels are the values. So basically the labels are also this trick. So basically it tells you if the car is yeah, valuable or not valuable or things like that. So the data set is here. It's very simple in that there is not much correlation between the different variables. So the number of doors doesn't correlate with the price of the car, apparently. So it's actually quite nice. Like for instance, in this example, if the variables were like correlated with one another, it would have been a bit different. The decision tree would have looked a bit more complicated. But here in this example, there is not much correlation between the different variables. So the data set is in this text file. We download it temporarily, and then we'll run the decision tree with it to see how it works, right? So let's import some basic libraries. So these are the run anyway. Yeah. So this cell, if you run this cell, it's just going to temporarily make a copy of the data into this repository. Actually, I suggest that you copy it to your own drive. I think you should do that actually for this one. For any notebook that requires downloading and saving a copy of the data temporarily, I think you need to copy the notebook to your own drive. So can you do this? Can you click on this? Yeah. Are we all good? Okay, so let's run this. This is gonna copy the data in this folder, temporary folder. Now we can load it with the pandas. So I think in this course we're going to use pandas a lot. We're not going to have enough time to go over panda. I think you probably have some knowledge of panda and it's very well documented. If you want, I can share a link with you so you can learn more about pandas in detail. But yeah, we're not going to do anything fancy with pandas in this course. So yeah, so this basically reads the data and it assigns these columns to the data. So the first column is price, the next one is maintenance, like how much money you need to spend in order to keep the car in a good shape, the number of doors, the number of persons that you can fit into a car, the space for the luggage, the safety of the car, if it's safe, if it's not safe, and its value, right? So if you look at the so when you have a Panda data frame, so this is a Panda data frame. If you do this, if you do data.head, open parenthesis is going to show you the first 5 rows of the data with the columns and their associated values, right? So you have the price, you have the maintenance, number of doors, luggage, safety, and value, right? So all of these values are categorical. Categorical, as I told you already, categorical means that these are discrete. So they're either 0 or 1 or 2 or they're strings, right? So for instance, the maintenance is like either very high or high. So the different values for the price are like, so here you don't see really the different values. So these are all very high. And the luggages are, so this one are a small, this one are a medium. So what we need to do with this data is that we need to first map all these categorical variables to numbers before we run any algorithm with it, right? So first, it's always a good idea to shuffle the data, because if the data is not shuffled, if there is any sense of order in the data, and if you train a machine learning algorithm, the algorithm is going to learn the order of the data, right? So if all of your prices are ranged from very low to very high, that's going to affect the training of the algorithm, right? So it's always good to shuffle the data. So here's what we do. We just shuffle it. And let's look at let's run data.head again. Yeah, hopefully this is more shuffled now, right? So the prices, you have low prices, you have medium prices. So the number of doors, if you look, so you have 5 more, means that you have more than 5 doors. Actually, I don't know if that's, I guess that's possible, yeah. But then you have 3 doors, it's kind of weird. But then, so the number of persons, you have 4, 2. Like sometimes you have numbers, but sometimes you have like strings. More means more than 4, right? So we need to find the mapping between all these like words and numbers. Like we need to turn all of these words to numbers. So that's what we do here. Oh, okay. Sorry. So this is up to you. So you can also change. Well, it's good to keep the orders, right? So the prices are like very high, medium, and low. You can map very high to 3, high to 2, medium to 1, low to 0, right? So you can do the same with all these variables. And for instance, for the number of doors, sometimes you have like these are either numbers or these are either words. So if it's a word like 5 more, you turn it into 5. Or for the number of persons that you can fit inside the car, sometimes you have numbers, sometimes you have words. If you have a word, you turn it into a number. This is just a simple way of like pre-processing the data before running any machine learning algorithm on it, right? So if you run this, all the categorical variables that you have in the data are going to become numbers. So actually, let's do this. Let's insert another code here. So in Colab, if you click on this, it's just going to give you another line where you can insert a code in. And if you did do this, it's going to give you a line where you can write the text in, right? So here, if you do data.head again, so it all looks good. So you have so all the words are now just numbers, right? And now you can use this to train your machine learning algorithm. So before we do anything, before we do any machine learning, let's do some exploratory data analysis to see if there is any like relation between different variables there. It's always good to actually before rushing into running algorithms. You always need to build a good understanding of the data. You always need to spend a lot of time just working with the data, analyzing it, and like looking at it from different perspectives, make a lot of visualizations to actually build a good understanding of the data. Here we're not going to have enough time to do that, but let's just look at the correlations between the different features. So, for instance, I want to look at if there is any correlation between safety and the number of persons that is inside the car, right? Or if there is any correlation between value and safety, or value and price. So here, if you, so this attributes, so data is a Panda data frame, right? A Panda data frame has an attribute called core, and core is basically computes the correlation between the features, right? So if you run this, it's going to give you the correlation between the, it's going to give you the correlation between the different features in the data. So now let's look at this. So this is a correlation matrix. So what you see is the correlation between the different variables. So the diagonal elements are all 1, which is obvious, right? Each feature, it's highly correlated with its own, completely correlated with its own. But the different features can be correlated with one another. But what you actually see here is that other than the value, if you don't look at the value, the different features are actually not very correlated with one another. Like safety is not very correlated with the cost of maintenance. Or like the number of persons that you can fit inside the car has nothing, is not much correlated with the number of doors. Yeah, at least in this data set. But anyways, but if you look at the value is actually itself is highly correlated with the rest of the parameters. So can you say which parameter is more important is more correlated with value? With the value of the car? And which one is the least correlated one?
Safety.
Yeah, safety is the one with the highest correlation, and which one is the one with the least correlation? Number of doors. Yeah. Yeah, the number of doors is not very highly correlated with the value of the car. But what you also see is anti-correlation. So these numbers are negative, which means that if, for instance, if you increase the price of the car, its value is going to decrease. So this value is actually not really the price of the car. This is like value, like let's say it tells you if people are willing to actually like purchase this car, right? Like if the car is this means that if the car is very expensive, the people are not going to buy it, right? Yeah. Or if the maintenance cost is high, people are not going to buy it either. But people care really about safety. But they also care a lot about maintenance and price, of course, but yeah, but in an opposite direction. And the number of doors apparently doesn't matter much, yeah. So let's, yeah, so I've already done this actually. So okay, so let's fit a decision tree classifier to the data and see how things work, right? So again, like what we did in the previous notebook, we split the data. Actually, so yeah, so you have a data set, right, which has the features. The features are price, maintenance, number of doors, number of persons, luggage, safety, and the value that you want to predict is this column, right? So these are your features, and basically these are all your features, and these are your labels, right? So first we split the data into features and labels, right? So X, if you do this, this attribute drop, it basically drops this column from the data. So what you have here is that X is basically contains these columns, right? And y contains these columns, right? And then what we do is that, like the previous like in the previous lesson, in the k nearest neighbors, we split the data into training and test, right? Let's run this. So this puts 80% of the data into the training. So that's what you use for training and validation, and then 20% for testing the performance of the model. Yeah? So here, okay. So this is a different way of doing the cross-validation. It's like less, how do you say? It's much faster, right? So in scikit-learn, there is this function called grid search CV. Basically, I don't know. So do you remember how we did the number of, how we found the number of nearest neighbors in the previous notebook? We actually created a list of the number of nearest neighbors from 1 to 20, and then we wrote a for loop and said, for each of these nearest neighbors, compute the cross-validation score, right? Do you remember that? So here is much faster. So you can actually use this function to search through the parameters that you want to find the optimal value for. So the hyperparameters of the decision tree is the maximum depth. So here the depth of the tree is, what is the depth of this tree? What? Yeah, the depth of this tree, what is the depth? No, 2, yeah. So this is 2. So beforehand, so here, I perfectly know how to split the data, so I ended up with 2. This is kind of obvious. But yeah, the depth of the tree is a hyperparameter. So the depth of the tree is like the nearest number of nearest neighbors in the k nearest neighbor classifier. It's like a hyperparameter that we need to find the optimal value for. And how do we find the optimal value for a hyperparameter? By the k-fold cross-validation, right? So what this does is that it basically searches through all these depths. So the depth between 2 and 20, right? And then it uses 5-fold cross-validations, right? So 5-fold cross-validation, just as a reminder, is just this. You take a data, you drop this part, you train it with this, and then you compute the cross-validation with this one. You drop this part, and then you compute the cross-validation with this one, and so on, right? So this gives you 5 cross-validation scores. You take the average of the 5 scores, right? And then once you have the average of the 5 scores, you pick the model that gives you the best accuracy. It gives you the best accuracy in the cross-validation scores. And then, so that's what it does. And so when you do this, it's going to find the parameters. It's going to find the depth of the tree that gives you the best cross-validation score. And then once you have the best model, you need to fit it again with the entire training set, right? So if you run this, it's going to do this, and then, and now you can pick the best model. So the best model is the model with the depth of a decision tree that is 13, right? And then once you have this model, once you have found that the depth of the tree should be 13, you can run it again with the whole. You can fit it to the entire training set. Actually, we've already done that in the previous line, so you don't need to do this, right? So now let's look at the score in the test set. So if you do this, it's going to give you the score for the test set. It's going to be 95.9, like almost 96% accurate, right? So now let's learn more about the model, right? So we have our best model. Our best model is a model with a maximum depth equals, this is not 12, this is 13. 13, right? And then we fit it to the data again, to the training, right? And then the best model will have this attribute, is the number of features, right? The importance of different features, right? And now this allows you to visualize the importance of different features. So if you run this, it's going to give you the features that are the relative importance of the features in determining the value of the car, right? So for instance, what this tells you is that like the safety is the most important feature, and then after safety you have, actually no, the number of persons is the most important one, and the safety, and then so on and so on, right? Is that clear? So now we want to visualize. So as I explained in the beginning, we want to visualize how this splitting is done, right? So we want to know how this splitting is done and what values and where they were used in order to split the data, right? So how does it work? So you have basically, yeah, so in any decision tree, you have basically, as I told you again, so you have some nodes and you have some branches, right? And then you have some node, the top node contains the entire data, right? And then you branch it based on some criteria. So for instance, if here in this example, if x1 is greater than 0.5, you branch the data into 2 subsections, right? And then in one of the subnodes, if you're only left with one of the data, with one of the labels, this subnode doesn't need any further branching, right? But then if you have both of the labels, then you can go on with the branching, right? You can go further with the branching until you reach a subnode that only contains one of the labels, right? So there are 2 important concepts, right? So you have nodes and branches, and you have the depth, and the depth is something that you determine with the cross-validation score, right? So we've already done that, and what we want to figure out is that we want to know what criteria we need to use in order to split the data, right? So the criteria for splitting, that's one of the open questions, and the other open question is like, when do we stop? So the answer to that question is somewhat related to depth, right? So if you reach the depth of the tree, you stop, and then that is determined by the cross-validation score. But then how do you, when do you stop branching? Yes, basically you stop branching when you either reach the depth or when you're only left with one of the labels in the subnodes, right? And then so the remaining open question is the splitting criteria. So how does the splitting criteria works? So the splitting criteria works in the following way. So there are 2 important so there are 2 ways to basically split the data, right? So the goal of splitting the data can be either to maximize the amount of information that we have about the data, or we want to minimize the contamination, minimize the mixing between the data, right? So there are 2 there are two ways of splitting the data. So let's first actually visualize the model with the model that we've already trained, right? So let's visualize this. So here you can specify the features of the data, right? And then maximum depth that you can that you want to that you need for visualizing the data. So for here, for instance, you can change the maximum depth from 5 to 10 or from 5 to 2. So actually, I highly encourage you to change this maximum depth. So for instance, if I set maximum depth to 2, it's going to show me how the data was split in the first step, right? So let's do this. Yeah, so the maximum depth is 2, so the data was split according to the following criteria. So if is the safety less than 0.5, if it's true, then go to this branch, and if it's more than 0.5, go to this branch, right? But why was safety chosen here? Can anyone tell why safety is a good criteria for splitting the data? Yeah, it maximizes the Gini. It minimizes the Gini, but yeah, we haven't discussed that yet. But like intuitively, as we discussed before, ideally we want to end up with in a node that has that has only one of the labels, right? That only has one of the labels. So why is this a good splitting? Why is splitting based on safety a good split? Yeah, exactly, yeah. Because already if you split based on safety, you end up with a node that only has one of the labels, right? This is like a perfect way of splitting the data. So that's the ideal way of splitting the data. So here you go to this branch, then here you have still mixing between the values, right? So you have all the labels, in this branch, right? But then if you split based on this feature, number of persons less than 3, then if it's true, you end up in a sub node that only has one of the labels, right? So this is actually a very nice way of. So you basically pick the feature and a value that gives you a sub node that only has one of the labels, right? In other words, you pick the feature and a value that minimize the Gini coefficient. So what is the Gini coefficient? That's what we're gonna discuss now. So you can, I encourage you to change this number to actually it helps you gain insight about how the decision tree works. So like you can put it to 10. It's gonna look huge actually if you do this. Yeah, this is very big. Yeah, but it's 10. Maybe 10 was a bit too much. Let's do 4. Yeah. So you start with this feature and this value. You end up with a sub node that only has one of the labels, right? And then you pick the feature. The next feature is picked such that you only end up with one of the variables, and then so on and so on, right? Yeah, and then you continue this process until you minimize the mixing. Essentially, you minimize the mixing between the different labels in the data sets, right? Is that clear? So I think in the afternoon session we're going to continue with the splitting criteria and how it works, and then we'll move on to another lesson, which is about the model evaluation, how the model evaluation works. So I think it's a good time to stop now. And then we'll continue this There's not much left from this notebook actually, yeah, but then we'll continue it after lunch.